working? Okay, so let's have a look at the diagram again. Does anyone have any ideas why it should commute? Or why it shouldn't?
This is the reference not just the left-mount
The rightmost, which one? This one?
This, yes.
Oh yes, why is it an isomorphism? It isn't an isomorphism. There's just one isomorphism here, this one. And these this is an isomorphism as well. So basically, we have two ways of passing from this object to this object. And we need to know that both that the two are the same. Many suggestions. Okay, well, let's let's write the m part. And well, the m part is what is it? Okay, this is the same as this one, and then well, basically, very similar to the other diagram. Okay, so don't know why either of these commutes. I think it's probably a consequence of the definition, but I don't know how to why exactly this works. So let's just let's just say the questions and let's think and if I'm able to find the answer next week, I'll let you know. For the moment, these are just two diagrams which will help commute, but we don't know why. Okay, so but assuming those diagrams do commute, we have distributivity we have distributivity for the two operations which we have on the homotypic classes of maps from the suspension of X plus to a ring spectrum Y. Okay, so what else do we need? We also need relative cohomology. So Well, let's first recall how we define the cohomology of a space with values in a spectrum, not necessarily a ring spectrum. Let me call the spectrum E. Why E? Because E resembles H. And H is the letter we use for cohomology. So to make this similar to the usual notation, we do the following thing. So we take the suspension of x plus. If I don't take x plus, I need to write a tilde. And well, here minus star means we can apply the shift to either of the arguments, and so instead of just one group, we get a countable family of groups, and this corresponds to the star. Okay, so if E happens to be a ring spectrum, the cohomology of X of a space, not of an arbitrary spectrum of a space, is a ring. Well, at least the zeroth cohomology. How to turn everything into a graded ring. Well, we need to need to have a map which generalizes the one we use to define a product on E0. Okay, so where could we get this from? Well, let's recall that we do have plus. No, this is it. Sigma infinity x plus. So this is what we have. So we have this. And we want this. How to get this starting from this? Are there any suggestions? The formulas look similar. Not the same. Similar, but not identical. So what do we do? Yes, but we want to construct this starting from this. So what do we do? Well, let's rewrite everything. Well, so what do we have? We have sigma infinity x plus smash sigma infinity s m smash sigma infinity x plus smash this is what we have here on top, and at the bottom we have sigma infinity x plus smash sigma infinity s m plus n. Well, if m plus n are if m plus n are positive, we can just use use the formula as it is, and if either of the indices is negative, we interpret both. So we interpret the formula as just the sphere spectrum shifted to the left or to the right. So, if we have okay, I want to introduce shifts. I introduce them here, and now I want to multiply the m component and the n component together. The result should be in the m plus n component. Well, I use this. And so we get a multiplication from we get what do we get? Okay, so write the result here. Basically, the arrow goes in the wrong direction. This is what probably was confusing. Okay, so what do? We take f from sigma infinity plus m x plus 2y, and we have g infinity plus n x plus again to y, and we want to multiply them. The result should be infinity plus m plus n x plus 2y. If y is a ring spectrum. Okay, so we use the identities here, and well, the arrow now goes in the right direction, and we're able to use all this to turn the well, at least to introduce the product on every on the set of maps from all shifts of sigma infinity x plus to y. And the resulting product is associative, and writing y again. Let me correct this. Let's replace y with e. Okay, so these two properties are straightforward from the same property for x. X is an associative x plus is an associative monoid with respect to the wedge monoidal structure. Okay. Now, the next property is well familiar from the usual from the case of the usual cohomology. If E is greater to commutative, so is E of x. Well, let's try to see this at least for the zeroth cohomology. What? No, sorry. If so is E. E meaning our monoidal structure on spectra is symmetric, or at least in in the homotypic category. So we have an isomorphism between A wedge B and B wedge A. Well, let's use this isomorphism for A and B both equal E. So there is the commutativity isomorphism between E smash E and itself. And we require that after we apply the product, we get a commutative diagram. The product both here and here. Jipping is, does this make sense, or the sense has been lost long ago?
So E must be commutative for A star of S to be greater than
Yes. If E itself is not commutative, then it's hard to expect that the E star of X will be commutative. Okay, so let's forget about suspensions. Where do we get the commutativity for E from? Well, let's return to the general nonces. Okay, so suppose we have a symmetric monoidal category, M a commutative monoid. And C a co-commutative comonoid. Then Cm itself is commutative. So if both the monoid and comonoid, or monoid, don't know how to pronounce it correctly, if both are commutative, respectively co-commutative, then the monoid we get is commutative. And essentially the same proof works for when we include the suspensions, but we get plus minus 1 basically for the usual reason. So the word graded is important, as you know. It's hard to expect the cohomology of pretty much anything to be commutative on the nose, unless 1 happens to be equal minus 1. Okay, let me also mention the distributive law, which we started proving but didn't manage to finish. But not all hope is lost, and maybe we'll be in a better position next time to prove this. Which basically means that A plus B multiplied by C is AC plus AB. Okay, so we do indeed get a commutative ring. I haven't. I haven't really explained how to finish the commutativity argument. M is a commutative monoid. Very well, but I also need C to be a co-commutative comonoid, which basically follows follows from the fact that x plus for every space x is co-commutative. Okay, so we do get a ring structure if we take the cohomology with coefficients in the ring spectrum and the cohomology of a space. If we have an arbitrary spectrum which is not a comonoid, there is no sensible way to turn the cohomology into a ring. Only for spectra which come from spaces, there is a way to make it work. Okay, now now we need to say something about relative cohomology. Well, let's again assume that x comma a